Hello, my fellow YouTubers. This is Roy back again. That's the moon. Look at those clouds. It's nighttime. Thought you'd be able to see them better. Guess you can see them there with the moon. There's your clouds. Look at the space in between them. Let's pick up where we left off. I think the last conversation we had in regards to the resonator is we went over the quarter wave resonator, we went over the octaves, we went over the Schumann. And on the last part of the Schumann, overtones we went over. Last part of the Schumann on the fact that there's on average of 2,000 thunderstorms roll over the earth, producing some about 50 flashes of lightning every second. Each lightning burst creates electromagnetic waves that begin to circle around the earth, captured between the earth's surface and its boundary, about 60 miles up. Some of the waves, if they have just the right wavelength, combined, increasing in strength to create a repeating atmospheric heartbeat. Earth's heartbeat. That's what we're going to talk about. Known as the Schumann. Earth's heartbeat. Here's Earth. Here's ground. Here's your clouds. Here's your distance here. We're going to do a scaled map on a big piece of paper, and we're going to come back to what I'm going to talk to you guys with tonight. All right, so we're going to start off with the reasoning of the resonator. There's a strong data behind it, and we're working through it. Snap a photo there, bam, so you can read it. So we're going to start off with the spheres, the layers, okay? So the first layer is the lowest layer, and it starts at ground level and extends about 6.2 miles above the ground, and it's the troposphere, and it's the most dense of the spheres that we're talking about, and it's where all weather is in the first 6.2 miles. Now we're going to do the chart up here, and we're going to work through the chart on the actual layers, so we'll do a vertical chart as well so we can see the depth and see what's going on in nature. All right, this is interesting stuff. I love it. Hope you guys love it too. So we're talking 6.2 miles up in the air. The second one would be which we call the ozone layer. It scatters solar radiation around, UV, ultraviolet, and all that. It scatters it around. It's the stratosphere. Okay, it extends from the top of the troposphere, and it goes up about 31 miles. So now we're talking 6.2 miles up to 31 miles. So we're going to do that in scale, and this is going to be fascinating to me to show you guys this in scale, because you'll get a better understanding on top of the understanding why the resonator could be the heartbeat that taps into all this, and it provides you a generator at your house producing energy if you want it. There's more to it than that. I'm just saying that as the low end. The third one is the mesosphere, and this is where most of the meteorites that come in, they'll burn up in that when they hit that section. And it extends above the stratosphere to the height of about 53 miles above our planet. Okay, so about 53 miles up in the air, we're dealing with any kind of matter that comes in will most likely burn up. Not all, because of it depends on the mass. And then on the fourth one is the thermosphere. Um, it's 372 miles high. Okay, and the layers of very rare air, X-rays, and UV high energy radiation area. So 372 miles up. So you can see all of a sudden, in between 53 miles. Remember this, stratosphere to the height of above the planet, 53 miles. And then it goes from 53 miles all the way up to 372. Great conversations going on there. So there would be the space of nothing, okay? I would almost like be something, so far you could look at as the thermosphere is more of a radiant, can we call it plasma, maybe? I don't know. Leave your comments. The next one would be the exosphere, and this is the highest one outside of all of our spheres, and it gradually fades away into the realm of interplanetary space. And let's turn the page on that one here, because I picked up somewhere here over here, and in the exosphere this is the upper limit of our atmosphere. It extends from the top of the thermosphere up to 10,000 kilometers. That's 6,200 miles above the planet. So you can see that there's different layers and there's different things going on in each layer. Very interesting stuff. So the above the exosphere, there's space itself. But then you have the ionosphere. So wait a minute, hold on. So you're telling me that the ionosphere doesn't, where does it go in here? You got 1, 2, 3, 4, 5 layers. So we're talking from the planet ground on out of this circle, we have 5 layers. Of course, these clouds are overexposed, so they're super big. So they would be real small on that first 6.2 miles from the ground to there. There's your dielectric density. Remember, I said density, right? So there goes your troposphere, is the lowest layer. You know, it's the most dense all of the spheres. It is the most dense, that density, that moisture. We'll talk about that in this further down the topic here. So the ionosphere, why they're not showing that in 1, 2, 3, 4, 5, is because the ionosphere is not a distinctive layer like the others mentioned. Instead, the ionosphere is a series of regions, part of the mesosphere and the thermosphere. So if we're starting where meteorites burn up, so there's your thermal, right? And there's your thermal here in your thermosphere. And you're looking between 372 miles. Remember I said where the nothing is going on? We're dealing with heat. So in that area right there in our layers of our planet, there's your heat management there. There's a below and an upper. There's a high and a low going there. So pretty interesting. Leave your comments on that too. I know you guys love this stuff. I'm going nuts over here. So instead of the ionosphere is a series of regions and part of the mesosphere and the thermosphere. And we just talked about those two between where the meteorites burn up and that's about 53 miles up to 372 miles. So it leaves a good cushion. And you can see if we're dealing with heat there, that particles would have a problem there. It'd be like living in hell. Be always on fire because you're a particle and your resistance, and see my fingers going. So basically, you would just burn up, be like close to the sun. So we can turn the next page, and this gets really interesting because the ionosphere is, we're going to do a little snapshot of that so you can read it. Bam. So the ionosphere is an abundant layer of electrons and ionized atoms and molecules that stretches from 48 kilometers, 30 miles above the surface of the edge of space. It's about 965 kilometers, 600 miles overlapping into the mesosphere and the thermosphere. This dynamic region grows and shrinks based on solar conditions and divides further into subregions D, E, and F based on what wavelengths of the solar radiation is absorbed. The ionosphere is a critical link into the chain of Sun and Earth interactions. This region is what makes radio communications possible. This whole area right here is very important. It is so important, I can't even stress how important this area is, because this is where plasma is sitting. This is the elements, the carrier wave that comes from the whole enchilada down to the solar system that's keeping itself alive as it's traveling. Now, we're going to move on to the next page. And, oh, no, we're not. So, D, E, and F, based on the wavelength. So we stopped over here, and communications possible. So we talked about the ionosphere, and this is the upper limit of our atmosphere, and extends about 6.2 thousand miles, or 10,000 kilometers. I guess kilometers km, I'm pretty sure. How far up does lightning go from the ground? That was my question. And about 50 miles. So if our lightning from ground goes up 50 miles, we got to go back to the beginning of the list where it says 53 miles. And basically the stratosphere is your ozone layer, and it's scattering radiation. So it's also dealing with where did we leave off? So it's dealing with about 50 miles up. So that's the area on how far lightning goes up. So you look and you can see that area there. It's the kind of the belt where, sure, the lightning can continue itself up. There's really not much stopping it, except for that area can be controlled by solar masses. So because nothing else is in the atmosphere can stop it until it hits the ionosphere. The lightning can travel about 5 to 10 times farther than the cloud-to-ground lightning, reaching up to about 50 miles above Earth's surface. Very important stuff here. So you can see that there's a layer, and that's what I'm trying to introduce to everybody on my channel, that if you want to break free from the basic electricity, how it's powered, how it's given to you, and what you do with it, you first have to understand nature. And that's where Tesla comes in, and that's where Marconi came in on his wireless. That's where Edison came in on his transformers and his generators, and that's where Steinmetz came in and took Tesla's work once he finally got it working with putting AC out. Steinmetz came in and he figured it all out, what it does, what it will do, and everything, the reactions from it. So Steinmetz is one of the greats. So electrical charge is, I got to get into electrical charge now because we just left talking about up in the ionosphere. And electrical charge is, of course, built up in clouds by the motion of water and ice particles. Very important. Leave your comments. Leave your comments on that because bam, stop right there, leave your comments. Lightning moves these charges around. Lightning moves these charges around. Both why some lightning goes up and other lightning goes down isn't known to science, but it makes sense to me that the difference between the cloud and the ground is a difference in potential. Sometimes the ground takes charge of the high and the low, just like the dipole and oscillating rotation of charges. For example, if the cloud because it's moving has a positive charge at the bottom, the ground below will have a negative charge, which is its normal charge, low pressure. But if the cloud on the lower section has a negative charge, the ground will move the negative charges down lower, like taking two magnets and forcing them together. They don't want to do it. They don't want to move. They don't want to change, but they're being forced down only because that cloud its charge is it's forcing it down. So if it had a negative bottom, it's going to cause a positive to appear at the ground level. And it'll move negative charges down lower than normal, and the positive charges will be at the ground surface. That's where we're going tonight. Interesting stuff, because if you kind of put it together on the pieces that I'm putting out there to you, that the next thing I do is a chart, and that's going to kind of glad I got my wits about me. The stud buddy. Just bought one of these. It's got a magnet in it. You put it on the wall and find out where your studs are. Shazam! And it sticks to the wall, so you can just measure off of that your diameter. Anyway, man, that scared the heck out of me, that sucker. I'll post a video. I'll put some electric through this. I wanted to see how many poles is created, and I could say there's 8 poles. Do the math. 2 top, 2 bottom, 2 coils in the center, 1 on top, 1 on the bottom, then the coils there. So you got 1, 2, 4, 6, 8, 10, 12 poles. 12 poles, okay? Interesting, 12 poles. Mark that. Back to where we left off on where we started this video and to where we just left off here. It's information, and once I dig deeper into this, you'll see how we could resonate and connect into the region of Mother Nature and be in tune and be able to tell the ground what to happen. So the resonator will be an activator, a switching device, basically, to, well, for now, the bottom part of the cone will be the just above ground, but we'll put a ground plate in. So underneath the plate in the ground, the opposite charge will appear, just like I demonstrated in my writings here, that the underneath the cloud will have the opposite pole appear just like a dipole. It's creating a dipole, which it is a dipole, but it's switching. And that's why I said science really can't explain why lightning goes up and down, and it only makes sense that the cloud is dictating what is going up or down. And you can see the elevations of what the cloud is. They do vary. And you can see how far lightning goes up. And you can see the ionosphere is the area that this right here would tap into. You guys leave your comments. I'll post the video up on Big Juicy over here. Do I need to give you a little taste? You guys want a little taste? You guys don't want a little taste, do you? Do I have it all hooked up? I don't even know. Hell no. Stuff falling apart here. You guys want a little taste, don't you? So this is sick psychotic shit here, because I put 15,000 volts in here, and basically I put the primary down the bottom, so it becomes two pickups right here. I'm not putting DC into both of those, but you're going to see a positive come out of here, because this wire is the top part of this cone. This wire is the base of this cone. And then this wire coming out is the base of this cone. But this wire that I have sitting here is the pointed part of the cone that's inside here, which is the positive. So you got a negative going to ground. You got a positive here, you got a positive there, you got a negative here, and then these 360 turns of coils in between the two pickups here are also dipoles and also have juice on them. Let's see, I need to shake up my bottles a little bit. Saltwater bath, sitting in oil. These guys here, they're pretty loyal. They are a loyal bunch. They love it. And mix up some juice over here. All right. Well, damn, I can't believe I'm doing this. Fire hole! that end zone. Love the breathe. It's fresh air. Ionized. Leave your comments, guys. Peace out.